Thanks everyone, thanks for joining. Good afternoon. My name's Mark Mallin. I'm a structural engineer at our practice Shape Structures, working out of Cape Town. In the next 40 minutes, I'm going to give a brief intro to myself and our practice Shape Structures. I'm going to give a very high level overview of our work in Eurocode 8. I'm going to bring that back to our SANS 10160 Part 4 and highlight where the red lines of our code are and highlight what I believe are widespread concerns as to its application. I'm going to touch on low-rise masonry buildings we've been involved in and some high-level concepts there. And I'm going to make some concluding remarks on the state of things and possible ways forward. Okay, obviously, looking for a quote to start. The way to make a film is to begin with an earthquake and work up to a climax. I'm not sure if I can promise that in a lecture, but let's see where it goes. And before the earthquake, a couple of minor tremors. I haven't formally studied seismic engineering. I'm a practicing engineer. I'm a generalist. This lecture, to describe it as a technical talk, it's going to touch on some technical issues. It's going to touch on some wider issues too, and it's more, I see it more of a panel discussion. It's not handing over a how-to. It's some high-level commentary. My background is 7 years with practices in London and the Middle East, 10 years with Henry Fagan and partners in Cape Town, and the last 9 years together with Matthew Gray as Shape Structures. Again, working out of Cape Town, work with Henry Fagan, lots of projects, but working on the seismic side, on these sort of typical commercial Cape Town, buildings to the pre-2011 seismic code. And then with Shape Structures, taking, especially forward, another thing I want to touch on is we often hear, oh, computer analysis, don't rely on it. We love it, and we use it carefully. We're almost, there's a lot of talking. We're also almost sketching through structures. I describe it. That's elaborating it a bit, but we like our models, and I'd say you should be able to play your software like a piano. And a lot of what you'll see is this kind of structural storytelling. Well, you're not going to see that much of it. I'm going to just touch over it, but basically building a narrative, a storytelling of a structure, and iterating through designs, and away from the analysis, also in kind of a lot of sketches trying to describe concepts. And like I say, I work within Cape Town, South Africa. Be the odd building or two, and when I say odd, there's one at the top. Obviously, it's almost living in a concrete core. It's probably way up there on the spectrum of seismic when we get to that. And then down below, much of our work for overseas consultants, the vast bulk of it, supporting their teams, working with their teams, learning with their experts, and then bringing in all Matt's experience on geometry and fabric structures, right down to this, so we're going from a 165 meter diameter concrete museum on the left to this 6 meter fabric dome up in the Karoo. And a big part of that work for overseas consultants has been building on Matt's contacts with the consultants we both work for in the UK and their global projects. And particularly that's been that high-rise experience, and taking that into some of the redder areas of the Mediterranean map down there on the left. In fact, back to the source of some of the highest, of the word seismic. The classical scholars amongst you will know seismic was Greek for to shake. Those towers, they've typically been residential, 30 to 40 stories. You can see individual ones, groups of them. And again, working in Eurocode 8 with their teams, learning from their specialists, and hopefully in the background, not completely relying on that, coming back to what's out there in terms of literature. And again, my main point here is when our South African code was released based on Eurocode 8, 2010, there was very little literature behind it. There's this Backman book, 2002, incredible book with all its concepts, which much of the background was taken from. And later we're going through seismic design for architects of all people, incredible descriptions, well worth getting hold of. And then later these Booth books, the 3rd edition, actually finished in Cape Town. He notes that in the forward, but covering sort of global principles of seismology, seismic risk, and various codes across the world, a sort of overview, quite interesting, or very interesting. And then specific to Eurocode 8, again, we've seen this increasing drain on our practices, bank balance, buying these books and luckily having the time to read them. And again, especially I'll draw a highlight to Jan Vium's chapter of the background of SANS 10160 in 2009. And a lot of these, again, they're at least getting an example out there. They never, you know, they always sort of seem to fall short of the real world, but at least there's this gradual kind of support and interest in the background. And the latest there, obviously, the two ISTRA-T publications, 2022, some specific examples to Eurocode 8. Again, interestingly, falling short of actually a reinforced concrete core example. Anyone who finds that, please, out there in the public domain, please put it there. And again, with those books, it's not just reading them, it's reading the codes, it's talking about what they mean, talking about seismic principles. So again, a lot of our practice is a bit of head scratching. I get a lot of focused thought from the guy across the desk there on the right. And between us, hopefully we enjoy it. We love structural engineering and building, and we try and get do the best job we can. The talk is possibly going to ask more questions than it answers, particularly on the buildings currently likely most vulnerable to South African earthquake environment. So please consider it a work in progress. Again, it's more of something that's, even though it's going to finish at 2 o'clock or before, it's open for discussion. So let's start with an earthquake. Let's start with an earthquake that happens here in Cape Town tomorrow. Let's say that earthquake resulted in peak ground accelerations of 0.1 G to 0.15 G, as per our code. What are the consequences? We were okay, weren't we? We had a national design standard introduced over a decade ago, with some additions in 2017, that covered buildings for this level of earthquake. We interrogated it, understood it, and implemented it, fully aware of the red lines of its scope. We looked beyond it for those buildings that were beyond it. We appreciated that the code was never written to be back applied to any building. Its fundamental basis was to apply clear layout principles and constraints on the stability elements and mass distribution of structures in order for them to be within its scope. Key pieces of building infrastructure had been reviewed as part of the City of Cape Town's drive towards resilience. Hospitals, fire stations, schools, and again, just to drop off, if I'm chatting to a forensic engineer colleague, a forensic engineer amongst many other things, his feedback is of 7 schools investigated for seismic compliance. None of those 7 complied. And that's not old schools, that's schools built in this last 20 years when we should be improving our building stock. Under the banners of both inherent respect for value of human life and resilience, there had been instilled a culture of identifying and reviewing existing and proposed buildings, most at risk from the codified seismic hazard. Again, studies on our infrastructure, our interchange, the study that was done there, Coburg itself. And as that earthquake started, we all reached for our cell phone and downloaded the City of Cape Town's What to Do in an Earthquake Guide. What should we have done before that earthquake? Was it the case that all this had happened? Really? What had happened with our pre-1989 building stock? Do we suspect there's been a slack application of the code post-1989, post-2010? Driving around town and talking to engineers, there's other engineers, there's a definite uptick in an attempt at diligent design in amongst it, but quite possibly, or almost certainly, there's many compromised buildings that are out there and under construction right now. The gradual envisaged replacing, updating of the building stock with seismically resilient structures has likely not happened to the extent it was envisaged. Seismic history globally is frequently reactive, not preventative. It's easy to slip into this thinking in our low frequency intraplate seismic environment. We've got to be aware that the research shows that the frequency of earthquake isn't necessarily related to the magnitude. There can be infrequent, large magnitude quakes. And again, South Africa, we've got this general collective post-event reaction to things. Looking most recently at something like the Wuppertal fire, immediately, wonderful efforts to restore it. What could have prevented it? And in the wider public managing expectations, what were our clients, architects, government, wider public expecting? So remember, possibly few are likely to thank us post this event. And that sort of shortfall has been highlighted in various scope papers suggesting we were possibly not prepared, that this disconnect between code and practice was a real issue. At this point, I might dwell on the usual key themes of seismic design lecture, and rightly so. Maybe regularity, uniformity, etc., soft story, ductility, critical region, plastic hinge, behavior factor, overstrength, etc. I'd probably then skip onto more advanced methods of analysis, more advanced methods of reducing the earthquake effect itself, and I'd probably skip any real-world design examples. I'm assuming most of us have been there, got the CBD points, then got back to the office and thought, what do I do with this? Well, I'm going to touch on just those key high-level concepts. What's happening in an earthquake? We've got a fault, a rupture zone, seismic waves traveling through the ground before reaching a building site and subjecting that local ground to various motions. What happens to the building? If the ground moves rapidly back and forth, then the foundations of the building are forced to follow these movements. The upper part of the building, however, would prefer to remain where it is because of its massive inertia. This causes strong vibrations of the structure with resonance phenomena between the structure and the ground, and thus large internal forces. This frequently results in plastic deformation of the structure and substantial damage with local failures and extreme conditions collapse. And then top right, we've got that fundamental principle of what we're doing in modern seismic design. We're taking the structure beyond its elastic limit. We're introducing this ductility. We're letting it deform to absorb energy. And the key aspect of that is when we're reducing that force, it's still achieving close to this displacement. It's a plastic displacement that's constrained by, in SANS, the confinement rebar we produce, and similarly in Eurocode to a more quantified extent. And then down there at the bottom, we've got our typical shear wall or core. We're looking at its aspect ratio, height to depth. We know it's a vertical cantilever. And again, we're concentrating on that critical region at the bottom. We're wanting to avoid that brittle failure and give it this ductile mechanism, create this plastic hinge, and then protect the rest of the structure above. Again, quantified in Eurocode, qualitative in SANS to the greater extent. And another key factor there is below, for that force to get into that wall, the structure below it has got to be protected to an extent. And again, foundations, they're expensive, they're hard to repair. Typically, guidance will be to design that close to remaining elastic. And all that's resulting in our ductility, our behavior factor, 4 different materials modified for different levels of assumed ductility. And so taking that into our application of it on European high-rise, here's a typical model of where we might start. It's a basis of a structural model. It's not the structural model. It's starting to investigate that core location, maximizing the utilization of that core, looking at the aspect ratio of that core, getting gravity loads on it to try and locate columns as far away from it as possible, and working within that. Again, we know, here's a developer, he's got a prime seafront view, he wants to sell that front space. The cores, for all the best will in the world to do the most regular building, here the cores offset. Therefore, the mass is eccentric to that core. Therefore, again, that key reference response spectrum analysis method of Eurocode is picking up those higher modes and combining them statistically into a recognized way of picking up all those effects and reducing the behavior factor accordingly. And again, just briefly, it doesn't get plucked out of thin air. It's, we've got an idea of where we're going to start, and it's this evolution of a design, this and talking our way through it, tweaking this, tweaking that, and looking at the results, fine-tuning it, and getting it down to something that the whole design team is confident works. And there we are. Now, from all that, a very clear structural principle, arriving regular from top to bottom. So even where architecturally openings aren't required higher up, that gets made as a dummy opening with a non-interacting structural masonry infill. these and back to the principle of capacity design, all the ductility on these cores, we're looking at coupled wall systems. We're introducing what you can look at as a fuse. So it's not just ductile at the base. There's our critical region of EC8. Each of these coupling beams is designed to fuse and give additional ductility to the structure in a ductile manner, and then push everything else that's a brittle failure mechanism beyond that. And down there at the bottom, we've got our elastic region and foundation. And then very briefly, now we're taking that core, we're taking the individual piers of that core, top left, we're plotting various envelopes with the tension shift, with all these extra bits to make sure that the hinge is happening where we want it, it's protected below it, and it's comfortably beyond that, going right through the rest of the stack. And then taking the coupling beams between those piers, we're looking at, we've all got our coupling diagram in SANS. We're seeing that appear sometimes in Cape Town. Why is it there? Because these are big, again, we know it depends on the aspect ratio of the beams. We want them, that they're going to behave in shear. We need that shear failure to be ductile, therefore the diagonal reinforcement. And again, you can see, even with these, 600, 700, 800 thick walls to the base of this tower, there's a lot of coordination required to get that kind of steel in. And again, we're in Eurocode. That's for a high tower, we'd expect that to be the process that has been followed on the majority of recent Cape Town high-rise towers to an extent. It's obviously not covered in the code. It requires you to go beyond it, and yeah, there's a lot there to work through. And having done it, it's almost resistance training coming back to SANS 10160 part 4. There's a lot of understanding and interrogation of concepts that made it a lot clearer to me from here, coming back to projects in Cape Town. And the key thing here is, starting on the right of this diagram, here's our response spectrum, the various ground types. It's our design response spectrum. We might adjust it actually on a 30-story tower, but it's lying right out there, way on the last sort of part of the spectrum. And as we come into Cape Town, we're coming to the limit of SANS 10160 part 4. We're finding this hazy red line, if you like, or red line, if you want to be strict, on the limit of SANS 10160 part 4's scope. And again, as we go up that line, we come in with stiffer buildings, more resonant with the ground they sit on. We can see right up there, beyond rock, all these soft materials, these things are picking up serious resonance with the earthquake, and they're naturally stiff and brittle, and therefore they're recognized as, as the most vulnerable, and where some of our local focus on concepts and peer review has been. So 2 high-level examples of that follow. And before that, why might it be that at times our standard is not applied or misunderstood? So let's just drop into that. It's this key, again, the first page of these PDFs. We're very quick to skip to the juice, but let's look at the scope. This part of SANS 10160 provides strategies and rules for the design of buildings subject to earthquake actions, primarily to safeguard against major catastrophic structural failures and loss of life, not to prevent damage or to maintain function. So we've got our 1 in 475 year no collapse requirement. That is, the building allows escape, but major repair or demolition is required. And then implied in SANS, it's explicit in the background to SANS, it's explicit in Eurocode. We've got this 1 in 95 year damage limitation requirement, where deflections are limited to minimize damage, and the building is very likely still serviceable. Now, that's an accidental ULS, so all our partial load factors are sitting at 1, and furthermore, our material factors may also be, they're codified as being less conservative. So compared to any other ultimate load case, we're down here on an accidental load case. All the meat is taken out, and again, just to touch on this skepticism that this isn't real. It's when it happens somewhere between that 1 in 95 year and 1 in 475 year. The building requires repair or demolition. So looking at schools, unreinforced masonry. Again, I'm not a masonry expert by any means. It's probably my least material experience. But we know unreinforced masonry doesn't mean completely unreinforced. It's bed joint reinforcement to minimum levels. We know the shear values on that masonry depend on the vertical load, it's pre-compressing it and mobilizing that coefficient of friction. But we're also concerned about what's the interaction as soon as we put slip joints from the brick to concrete slabs, as soon as we put damp-proof courses in there. And yes, there's some guidance to do it experimentally in the code. There's University of Stellenbosch's research on what those values might be, generally concluding they're pretty low. And again, something that we want to rely on for a building as important as a school. And we're also seeing that in our safety verification, we're beyond the sort of simple rules in SANS. The verification of that building safety against collapse should be explicitly provided. We'll do that by referring to SANS 10164 part 1. We've obviously got our kind of parallel Eurocode masonry code as well, and we're reducing that material factors compared to what we do for wind or other shear effects. So looking at a school, long, linear, that's what we typically might see. And here we were working with another engineer and talking with them about their ideas on the seismic effect. And again, breaking this into these individual, quite regular blocks, good aspect ratio, trying to get the torsional centers of these as close to the mass as possible. It's not ideal, but it's very, generally it's pretty symmetrical. It's pretty comfortable, especially over these 2 stories. And why the reinforced concrete shear walls? Again, going back to this idea of deformation, that if we're going to have, well, firstly, it might have been a desire to do this in clay brickwork and mobilize that as shear walls. But again, with the unknowns, we were very concerned about that. And again, introducing these. Now, if I design my shear wall with my behavior factor of 5, back to that, it's going to deform the equivalent of what that force would have been before it was reduced because of the behavior factor. So we're actually trying to restrain that deformation, not mobilize the brickwork, and we end up with a much more robust building structure that, again, through the analysis of each of these blocks individually, actually very simple model, just those red structural elements with their structural properties, the rest of it just as mass, and a quick way just to work through different iterations of that, different ideas of element thickness, etc., and bringing that down. Another interesting exercise to do is to take clauses in SANS 10160 part 4 that were non-conclusive or open-ended and just compare those with Eurocode. So for example, now we've split this building into these individual blocks. We're reading the one part of SANS that we know possible pounding, seismic pounding of those individual units should be considered in the design of joints. There's no further guidance on that. To Eurocode, seismic joint condition in the no collapse requirements and the specific limitations on what that displacement can be. And so between all that, we end up with a wall that's comfortably behaving, taking that seismic load elastically. Therefore, we're comfortable that the brickwork isn't getting mobilized. And actually, after the fact, we went, reading through the back catalogue of SAISA Journal. There he is, Jan Veerm, 2007, wonderful paper on conceptual design of structures for seismic. There's the diagram. It's there back in that 2002 Swiss document too. And we're reading, again, just to reiterate, building masonry construction are relatively stiff. They have a high first natural frequency, low period. So the lowest modes of vibration are located in the high region of the design response spectra. Masonry structures are thus subject to high seismic forces relative to their mass, in those high percentages. Masonry construction is brittle, does not allow much dissipation of energy. Ideally, masonry structures should be reinforced. That means vertical reinforcement as well as horizontal. Not a preferred construction method in South Africa. That's a lot of time on site, a lot of supervision. Whereas with the wall, it's more of a one visit, one inspection. And that's being optimistic, but it's at least the critical bit is focused. The connection of those diaphragms to that wall are certain for the total force in the diaphragm. We're not relying on that brickwork connection. Shear walls should be dimensioned with sufficient rigidity, and they must be able to resist the seismic forces by staying elastic without plastifying the reinforcement. The horizontal displacement of the structure must not exceed the possible displacement of masonry walls. And there's not our project, but driving around Cape Town, there's another one out there in the wild. someone else reading the guidance, and there's that wall clearly in that 3-story structure, residential structure. Then again, but often, we know we're seeing these rules for simple masonry buildings. They're basically cut and pasted from Eurocode. The background to Eurocode says they're conservative. And a better man than me, or woman, is going to, a better person, engineer, is going to write a parametric program that actually translates that to a realistic building. But you can see, you can start to play about with those values. And again, if we're doing a deemed to satisfy design, or we're avoiding the specific variation for residential structures, there's some guidance there, but you've really got to be, I think, quite disciplined to work within it, and that's then feeding obviously all the outer plane stability of those walls and other deemed to satisfy rules for masonry. Where then, the second of these projects is this low-rise multi-residential. We're looking at a 2-story building where, again, we were asked to, in a way, model it seismically and advise on this. And again, here it's these big outer plane failures of reinforced concrete walls. Are they part of the primary structural system? Are they not? We tried to use, this is obviously long party walls now. We think they were mobilizable as masonry shear walls, but again, we've still got this concern over the damp-proof course performance. And this is, it's not a small structure, it's quite big. It's big numbers, it's big forces. So again, here's this principle of a series of orthogonal reinforced concrete shear walls distributed across that building plate. And again, here's our other theme of that we find talking to others and people who are trying to design for this. We can put these walls in, we get these big base moments. How do we deal with it? Well, here was the idea of at least getting this ground beam in there, mobilizing the party walls and resistance a lot of that uplift. So again, you can see that just going back to that plan, you can see those H's. There it is in PD. Again, key guidance on even the thickness of the structural RC topping coming in from Eurocode 80 thick. That was asking in that case. Again, that's open to correction. And then from there, from that guidance, we get to our typical multi-story block work. And again, I think this is the building type that, again, most of us have concerns about in Cape Town. It's always the one that's brought up in conversation, that if we're looking at this, where are the shear walls? Where's the verification of its rational design? I'm not saying it's not possible. I'm not saying it doesn't exist, but the one-way, again, now we've got the damp-proof course issue, the slip joints. We've got the one-way spanning precast. We've got the diaphragm action tie-ins. We've got the tying in of that gable eventually to the roof to, again, stop this outer plane moments. And again, going from those 2-story buildings to the 4-story, where's the cutoff where someone actually needs to get in and see this housing as a product? We're going back to the towers compared to those. Let's say a development's got 200 units, 90 million rand. That's 600, 800 lives potentially within that space. It's a 100 million rand project. When do we actually get a product review, a project recall before we roll out more of these? And hopefully there's something in process currently with City to at least mitigate that and address it. And what's leading to that in the background, briefly, it's this process of self-certification. As a PRN or a professional engineer, it's knowing what you can't do. And currently there's no check of rational design in South Africa today. And again, but right back to the first of our technical talks this year, Alex and Emmanuel, has a structure failed, and the difference between collapse. Has a structure failed to meet the code, doesn't mean it's collapsed. Again, these forces are coming only once they're tested. And building on the sort of precedent is a precarious thing to be doing. So that could possibly be said even more strongly, but let's not start with an earthquake. Let's not repeat the history of recent other cities, countries, etc., and even the Cape Fold pre-Toolback series events. There's a history of, especially this idea of legislation being in place, good practice being in place, and it being ignored. If you've going back through other events, it happens again and again. And is that the situation we're in here? How do we get all this good stuff that's coming out of academia, from code drafting committees, from geotechnics, even the recent issue of Civil Engineering Journal, you search seismic, you get papers on the soil structure interaction, trying to address that, the size of those foundations, liquefaction of soil in the Cape Flats. And again, between these design codes, where are the actual worked examples that are practical? Who can step in and provide those and make us feel more comfortable? And in terms of any, knowing that this exists through the project team, I think that, again, in the motivation of this code, it was always mentioned that it had to engage architects and get them on board to implement it. And the idea that it's a risk, also knowing that we live under this threat, psychologically, can we afford to look under the bonnet? And you could make a comparison to the Grenfell fire in the UK and all those properties that are sitting with that cladding, and it's a night after night thing. It does make it easy to sort of put it aside. Not easy, but you know what I mean. And then, okay, so now let's get capitalists, let's get purely financial. Our insurance industry, I pulled out my insurance cover. What is covered? Earthquake. What is not covered? Where any of the following cause or contribute to damage: defects in the design or construction of the building, or where the structure would not have been approved by the relevant local authority at the time of construction. Imagine putting that next to our map in front of clients and asking them, do you or do you not want this? And again, we again in our appointment, getting onto Form 4, we're going to say, we know fees are an issue. We know time to follow these things properly. So limit that scope to a building that's strictly within the scope of SANS 10160 Part 4 and highlight that beyond. And when we get to that form, signing off that completion certificate, what's that saying? We're signing off the structural system for which I have taken responsibility. It, to the best of my knowledge, has been designed and constructed satisfying the requirements of the National Building Regulations. Has it? And again, back to that, what we can, some positives and what we can do, looking at, again, this modeling and assessment and scientific investigation of the seismic risk in South Africa. I've also got to admit, when it gets difficult, when it gets tricky, just generally looking at, I too have had doubts. And I had a very fortunate meeting. He was very kind to give up a lot of his time a week ago, and that was Chris Palmer, who has put together in the background these three quite incredible volumes of following that through. Before I met him, what I would be saying is, to get on top of this, we've really got to focus all the work that's been done to say why this is a risk. And here, with a lot of work behind it, these three volumes addressing the basic seismology, our South African seismic environment, step by step, methodical, very, very good reading. And Chris has kindly agreed to make those free upon request. He is chrispalmer824@gmail.com. Mariette might put that into the chat. There it is again, chrispalmer824@gmail.com. And again, actually also in the background, there's a committee looking at the fudges on our map and our design. We know we bring in this redundancy factor to temper what was assessed in, again, I've very much concentrated on Cape Town here, but across the country, other areas of risk, we know Jagersfontein in the red spot there, that's also actually a zone 1 seismic region. What would have happened to this poor dam then? But that committee is tidying up our maps, rationalizing our design approach, and I think that's a good effort to, let's hope it's a good effort to conclusively agree what we face. What else is out there? Again, well, what else can we do? Let's release real South African worked examples for peer review and wider distribution. Again, very easy to say, very easy to ask for, much harder to produce. What else has changed since 2010? This online videos. we're seeing topic by topic, those by Richard Walls, incredible, University of Stellenbosch, really clearly going through things. And again, on a similar vein, about 2 years ago, this Design Arc, a Technical University of Delft, there's a whole series of YouTube videos really going from the fundamentals through to different material approaches. It's very impressive. And again, where's the guy in the world who explains this the most clearly and gets this to us? Then we've got, again, this lack of authority checking. How do we compensate for that? Should our structural designs be open source? At least our public buildings, should we be able to access the structural drawings for those, the design assumptions, the behavior factors that were assumed? And again, as an example of that, you can take not a seismic collapse, but seems to be a lot, certainly a whole, again, as all these collapses are, a whole lot of contributory causes. But that Miami, Florida Surfside, within after collapse, its drawings are in the public domain, and very rapidly you can see that wind in that east-west direction, and that apparently those 2 shear walls in a 13-story building. It's quite incredible. And again, where's the Rolls Royce of looking at risk? Seemed to be, this is from a year or 2 ago in the Arab Journal, and Groningen, obviously in Europe, fracking and its influence on changing the seismic environment, and they went building by building with all sorts of quite incredible modeling. So it's Rolls Royce stuff. This was every building. Yeah, is there motivation for just a couple of our key buildings, just flying over Google Earth, driving around, seeing what we think is most risk, and some impetus from the city to actually just commission and again say, and there's some shake table work being done. There's obviously the Stellenbosch document on masonry, but again, it's theoretical. It's not addressing conclusively where we stand, and it's always raising, what about the tie-ins of diaphragms? What about the outer plane stability? It's certainly not a sign-off by any means. And then this wider education with respect to risk, the dissemination of that to architects, government, property developers. Again, are we poor at sitting down at the client meeting, holding this up and saying, boom, 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 this is what's required. I'm not going to veer from it. And I know, that's what we should be doing. And then with that conversation with others, the whole story of carbon footprint, climate emergency, general concern for economic use of materials, value for investment, durability, and resilience. Again, I'm all for let's build things that last, that get used, that are resilient, that are safe. Let's build well. And if we're not fully signing up to the total hair shirt, but especially if we're not signing up to these safety aspects, what are we saying? How close are we getting to the message on the right? And again, it's not just the structures. We're seeing this quote in Conceptual that the mayor says they had 2 earthquakes, the 8.81 and the following social earthquake. What's happening to our water supply, our electricity? Again, all those ideas of concepts of resilience that we'd like to bring on board. So in conclusion, again, it's very easy to get drawn into this topic, kind of hypnotized by it at the expense of everything else. We know there's all sorts of other things feeding our structural design. Gravity's on 24 hours a day. Wind, when it comes, at least there's a warning. There's maybe 2-3 days before a storm comes, when, even though it's sweeping across a region, it can take. A fire, awful, but tends to be a local event, and not destroy, especially these days, not destroying everything in one foul swoop. Earthquake, there's no warning. It comes and it takes everything out. And really, that's the concluding note. Thank you.